Rutherford model, we have seen that this model gave the concept of nucleus, entire positive charge and almost all mass of the atom is concentrated at the center. He also estimated the size of the nucleus. But though it could explain the observations of Geiger and Marsden experiment, but it also failed to explain the hydrogen spectrum. Hydrogen spectrum means, see, spectrum is orderly arrangement of radiations. For example, if we want to take the spectrum of light from a bulb, we heat it, we pass current, the filament is heated, it emits radiation, and if we take a prism and pass these radiations through a prism, you take a prism and put it in front of a bulb. So radiation passes through it and you can see all those radiations in the light coming out of the prism. That is the prism. That is the spectrum, emission spectrum. Okay. Now same way, hydrogen spectrum means we take hydrogen gas in a flask, sealed flask, we heat it, and then the atoms are excited, electrons move to the higher states, then they come back and emit radiations. It was not known actually when Rutherford model was given. Hydrogen was found to emit radiations and there were specific wavelengths in it. For example, there is a wavelength 656.3 nanometer. Then there is another 486.1 nanometer. These two wavelengths are found in the hydrogen emission spectrum, but in between there is no line. So we don't find radiations of all possible wavelengths in emission spectrum of hydrogen. In Rutherford model, it was said that the electron is moving, its motion is accelerated motion, so it should continuously lose its energy and should give out radiations of all possible wavelengths. So it means Rutherford couldn't explain the hydrogen spectrum. Bohr explained the hydrogen spectrum and gave certain assumptions which we can call postulates of Bohr's atomic model, and on the basis of these postulates he successfully explained hydrogen spectrum to a large extent. Eventually there were some other objections, even this was not found to be sufficient to explain it entirely, but to a large extent it explained it. What were the postulates? One is that electrons are moving around the nucleus in circular orbits. The same point which was stated by Rutherford, that entire mass and positive charge is at the center in the nucleus and electrons are moving in circular orbits. And the centripetal force is being provided by the electrostatic force. But the important point that he added is, so first we can say about this circular orbits. Second postulate was that all orbits for the electrons are not possible. Electrons can be in only certain orbits. He named them stationary orbits. And electrons in these have fixed energy. So he didn't explain the reason for it, but he said that electrons are moving in circular orbits and they have fixed energy. They are not radiating. He gave the condition for these. Only those orbits are possible in which the angular momentum of electron is a multiple of h upon 2 pi, where h is Planck's constant. N is just a number, 1, 2, 3, 4. So only those orbits are possible in which the angular momentum of the electron will be a multiple of h upon 2 pi. So he quantized even the orbits. And for the emission of energy, he said energy is given out by an atom when the electrons move to one fixed orbit to another fixed orbit. So from one stationary to another. Say for example, if it is coming from one level to other, we call them E2, E1, the energies of the electron in those two orbits, then this will be given out in the form of a photon or radiation. So hc by lambda. Now, using it, he explained the spectral lines obtained in hydrogen spectrum. Now, the wavelength of the radiations emitted in hydrogen spectrum will also depend on the energy of the electrons in the two orbits. E2 is the energy of the electrons in the higher orbits. E1, the energy of the electron in the lower orbit. He calculated this value. E is the sum of kinetic energy and potential energy. So half mv square kinetic energy. What this E will be? Half mv square kinetic energy of the electron plus potential 1 by 4 pi epsilon naught Ze into E upon R, Q1, Q2 by R with a minus sign, attractive force. This is the total energy of the electron. So we can calculate this E2 minus E1 and then find out lambda. Now our aim here is to find out what is the value of velocity of electron in any orbit and what is the radius of the allowed orbits in an atom. So let me calculate and then find out the expression for lambda. Nucleus and electron moving around it. So 1 by 4 pi epsilon naught, charge on the nucleus, charge on electron, R square. This is the Coulomb force and it is providing the necessary centripetal force. And the condition given by Bohr is mvr is equal to nh by 2 pi. Substitute these. You can substitute V from here to here or R from here to here, whatever way. We have to find out the values of R and V. You can do these steps. I am leaving that part. Just substitution, nothing else. So R comes out to be this value and velocity so this is the radius of an orbit and this is the velocity of electron in an orbit. Depends on the value of Z, E. So if I substitute these values, epsilon naught, H, pi, M, E, these are the constants. Z and N variables. So it comes out to be 0.53 N square by Z angstrom, and this comes out to be around 2.18 into 10 raised to the power 6 Z by N meter per second. You can learn these expressions directly. They are very helpful in competitive exams at least, because you need not learn these expressions. Okay, you can keep in mind directly. So this is the radius of any orbit. When we are talking about the hydrogen, so Z will be 1. And then putting the values of N, we can find out the radius of the first orbit, second orbit, third orbit, and so on. Same way we can find out the velocity of electrons in different orbits. First orbit Z1, N1 for hydrogen. Second orbit for hydrogen, N will be 2, and so on. Okay, now we have R, we have V. But we need the value of total energy of electron in the orbit so that we can find out the value of E2 minus E1. We have to find out eventually 1 by lambda. We are finding the wavelength of the radiations emitted. Okay, so R and V. V is Z square upon 2 epsilon naught Hn. Substitute these values again and find out the kinetic energy. Half mv square, put the value of V here, it comes out to be m Z square E4 upon 8 epsilon naught square H square N square, and then potential energy 1 by 4 pi epsilon naught Q1 Q2 by R. Substitute the value of R with a minus sign. M Z square E4 upon 4. Potential energy is minus because the force is attractive. Okay, so this is the value of kinetic energy, this is the value of potential energy. We can see the relation between the two. Pi Z square E4 epsilon naught square H square N square, this is same. The only difference is here it is 8, it is 4. So potential energy is double. So actually I can write potential energy is twice of kinetic energy, but minus sign. If I find what is the total energy, sum of these two, kinetic plus potential, it comes out to be m E4 Z square epsilon naught square H square N square, these all remain same. The only difference will be 1 by 8 minus 1 by 4, or 1 by 8 minus 2 by 8. So this will be the energy. So potential energy is twice of kinetic energy, and total energy is same as kinetic energy but with a minus sign. This has important significance actually. Total energy minus means the system is bound. Energy of the electron negative means electron is bound to the nucleus. The moment it becomes 0, it means now the electron is out of the atom. This is what we call ionization energy. So ionization energy will be plus of this term. It is just like we did it in escape velocity. So long as the energy is negative, the system is bound. The moment it becomes 0, it means the system is no longer a bound system. Kinetic energy needs to be needs to be less than potential. Potential more, because if negative is more only, then the system will remain bound. So potential is double of kinetic, but minus total energy is also minus. And this also 1 by lambda we will find out using this expression only, but for again numerical purpose you can substitute all values except Z square and it comes out to be minus 13.6 Z square upon N square electron volt. This is an important and very useful expression. We shall be using it directly in numericals. So the total energy of one electron in its orbit around the nucleus is minus 13.6 Z square by N square. So when we will talk about hydrogen, Z is 1, N is 1, first orbit, second orbit, it will be 2, third orbit 3. So you can see even the energy of the electron can have only certain discrete values. It cannot have all possible values. Okay, now using it, find out E2 minus E1. E2 minus E1 is Hc by lambda. So 1 by lambda is E2 minus E1 by Hc. So it is 1 by Hc and E2 minus E1. E2 will be minus m E4 Z square upon 8 epsilon naught square H square N2 square minus E1 minus m E4 Z square 8 epsilon naught square H square N square. Just substitution, the expression seems very complex and lengthy, but actually it's for all, just a substitution work. Okay, I can take many things common out of it. So it is m e4 z square upon 8 epsilon naught square h cube c. This much is common. And here it remains only 1 upon n1 square minus 1 upon n2 square. That's it. 1 by lambda is called wave number. 1 by lambda is wave number, and here also we have a constant. This is called Rydberg constant. So this is the expression Rydberg's constant. So z square 1 upon n1 square minus 1 upon n2 square. So if now we substitute values of n1 and 2, we see that lambda cannot take all possible values. It can take only certain discrete values, and the values that I told you, they all actually are found to be satisfied when we use this expression. Because now the lambda will depend. What is the way of getting the spectrum? Take hydrogen gas in a sealed flask, we can heat it, or we can also do the electric discharge, but any method will do. And then the atoms are excited, they move to the, electrons move to the higher energy states. While coming back, they will give out energy in the form of electromagnetic radiations. We can pass this through a prism, and they will be separated. Okay, and it is found actually that these radiations are not just confined in the visible range. They are in UV range also, they are in UV region, they are in infrared regions, they are also in far infrared regions. So see from here, E2 minus E1 will determine the value of lambda, and using this I can now have a diagram showing the different transitions. This is 1, 2, 3, 5, 6, 7, and so on. Okay, these are the different energy states for hydrogen. The separation will keep on decreasing. How do we find out the energy? Minus 13.6 Z square by N square electron volt. So you can even write the values of energy. 1 will be minus 13.6, 2 will be divided by 4. So, and now when atoms are excited, it means now electrons move to the higher state. From 1 to, they move to the higher state, 2, 3, 4, 5 and so on, right? And then they will come down. Now lambda of the radiations emitted will depend on these two levels between which the transition is taking place. And depending on the final level in which they are coming, this spectrum has been divided into 5 series. If the electron is finally coming to n is equal to 1, we call it Lyman series. And so on. So this is Lyman series. So Lyman series, the electrons are coming from 2, 3, 4, 5 to 1. All these radiations will have different wavelengths. So when transition is from 2, 3, 4 to 1, then it is Lyman series. And which one will have maximum energy? Maximum energy. Maximum energy is, more is the difference, more is the energy involved. So when it is coming from infinite to 1, it is maximum, and the same will have minimum wavelength. Maximum wavelength will be when it is coming from 2 to 1, and this will have minimum energy. Same way we can calculate for each. Minimum wavelength when the two levels are closest. Energy will be minimum, sorry. Wavelength will be maximum. And infinite to that level, maximum energy and minimum wavelength. Lesser is the separation, lesser will be the energy. Okay, this is Lyman. Balmer is this. This is Balmer. So finally, if the electron is coming to n is equal to 2 state, it will be a Balmer series. Then we have Paschen, we have bracket, and then one we have P fund. So Lyman, Balmer, Paschen, bracket and P fund. These 5 series are obtained. This is in UV region, this is in visible region, this is infrared, and these are in far infrared regions. So the radiations are not just confined to the visible region, they go beyond it, UV region as well as infrared regions. Now this theory could successfully explain the spectral lines that we get in hydrogen spectrum to a large extent. What were the problems related to this theory? You will do it in higher classes. So that's enough for this class. Thank you.